Swayam Prabha. Digital India. Educated India.
So, we have seen that it is possible to utilize the principle of 2 degree of freedom system in neutralizing the vibration of an object. To demonstrate how this kind of tuned vibration absorbers are designed, we will take up a specific example. So, this is a vacuum pump. We need not go into the details of the story behind it. The main thing is that the machine, which is being driven by a motor, is suspended or supported on 2 springs, and it is capable of making vertical movement, whose frequency will be same as the unbalanced force which is generated in the machine, maybe a vacuum pump of cylinder piston type. And so, we have to design a vibration absorber vibration absorber means is another spring mass system to be connected here or here. So, what is given in this case is that the machine runs its nominal speed at 1500 cycles per minute. You can easily find out the corresponding omega, and obviously the frequency of the force generated will be same, that means this relates to omega. The magnitude of the force at this speed is 50 Newton, and the rattle space is nothing but twice the amplitude of the absorber mass, wherever it is, if it is here or if it is here, depending. I have kept larger space here. So, the maximum amount of displacement MA can have on both sides of its equilibrium position, that is called rattle space, that is given as 15 millimeter. Now, I hope you remember that it is also very important to see that after adding this absorber mass or absorber system, the natural frequencies of the resulting 2 degree of freedom system should be wide apart, and in this case it has been told that omega natural frequency 1 should be below 1350 ppm, and omega n2, the other larger one, should be above 1650 ppm. We can easily find out radians per second, you can convert. So, that means the 2 natural frequencies should correspond to values, they should lie outside this region, where the nominal operational speed of the system is this, and obviously we know that this will be also the resonating frequency of the primary system. So, you have to find out Ka and M three conditions will be, one is that square root of Ka by Ma is the natural frequency of the absorber system, should be equal to the natural frequency of the original system, and which must also match with the operating frequency, which is 1500 ppm, that is equivalent to, I think, 157 radian per second. That is one condition. Second condition, x a must be less than equal to half into rattle space, that is 0.15 millimeter. I think let us keep it at millimeter only. And third thing is that omega n1 and omega n2 must lie outside this region. So, how do you proceed? The first thing will be, we have found out and we know that omega A is equal to omega n equal to 157 radian, so which is same as square root of omega is actually omega Na. Next, we also know that omega n1 by omega n equal to psi 1, omega n2 by omega n, we have found out as chi 2, and we also know next. So, therefore, what is done generally in such cases, that we first take a trial auxiliary system. So, we first attach a trial absorber, and when we attach the trial absorber, say of mass trial is say 0.1 kg. Now, whenever we say that it is absorber mass, it has to be tuned. So, though it is not mentioned, it is obvious that KAT should be such, it should be omega n square into MAT, whereas omega n is the operational speed, that is 157 radian per second, and trial mass is there. So, this will be, this can be found out. We will just keep it, we will not necessarily. We also know that once we attach this trial absorber, the resulting omega n T1 and omega n 2 T are (1400) ppm and 1607 ppm respectively. Since the two resulting natural frequencies are not outside the region, obviously this trial absorber is not satisfied. But we could with this experiment we can take the result. That means omega n T 1 is this much So, therefore, trial value of chi T1 will be so that is equal to and chi 2t we can find out either as which will be 1.071, and we also know that this is nothing but 1 by chi 1 t, because chi 1 into chi 2 must be equal to always 1 that we have derived. We can mention this also if necessary. We should also mention that chi 1 and 2 can be written as half So, now we know the trial values of this, and from this we can easily find out the mass, because we know that trial value of this, which is nothing but trial value of the absorber mass by m, will be nothing but from this relation we get chi 2 trial minus chi 1 trial square, which is 0.01. So, we can still we cannot, we can definitely find out from this what is the value of your original mass. This can give us easily, because m of the original system is nu trial into m a trial. If necessary, you want to find out, we are not required to do it, but we can easily find out how much it is going to be. Anyhow, we will not need do that. Rather, let us find out that if we want to now find out the design absorber, the final one which we want to do. Now, let us, we know there are many conditions, many constraints. Let us start satisfying one constraint exactly. What we may say that, okay, let us take this constraint to be satisfied. That means, with design absorber, chi 1 d will be 1350, which is just the limit by 1500, which is equal to 0.9. And obviously, with this you have to find out that chi 2 d will be then simply 1 by chi 1 d, that relation, and that will give us, that will lead to omega n 2 in the design stage will be equal to, here actually this was design stage. So, this will be 1 by chi 1 d into omega n a, which is nothing but 157 radians per second, or which is equivalent to 1500 ppm. So, this will give us simply 1667 ppm. So, our when we put the we put a trial mass here or a design absorber here in such a way that when the two frequencies are splitting up, the lower frequency is just equal to this, then the upper frequency which we will get will be above this. That means the frequency condition is being satisfied. But there is another condition which you have to now see finally. So, two conditions we are satisfying, that is natural frequency is same as the exciting frequency and also which is equal to the natural frequency of the original system. We have also now put a design absorber in such a way that if we put a design absorber to make the lower natural frequency exactly equal to the limiting value of the natural frequency to avoid any large oscillation when the exciting frequency varies, then the upper frequency is above the other range. That means we are satisfying that condition. So, the other condition, that is the rattle space, now we have to see. Now, to find out rattle space, we know we have to find out X A, and X A means the amplitude of the absorber mass is simply F0 by K A that we have derived in the previous lecture. That is, X A is nothing but so what F0 is given. So, we have to find out K A. If we can find out K A, we can find out X A. Now, how to do that? Now, you know that design value of this nu is simply design value of chi 2 minus design value of chi 1 square, and that is equal to since chi 1 is this, chi 2 is 1 by 0.9. So, we can easily find out this is equal to this, and design value of nu by trial value of nu becomes trial value of nu was, which is equal to 2.347. Now, since nu is nothing but ma by m, so nu d by nu t will be ma d by ma t. So, this will give us the design value of the mass, absorber mass, will be equal to 2.347 into trial value of the absorber mass, which was 0.1 kg. So, the whole thing is 0.2347. So, we have found out the mass of the design absorber, not the trial mass. So, once we find out that, we know the natural frequency. Since we know the natural frequency, we can easily find out the K. K will be equal to simply KD into 157 square, and that will be equal to that is the stiffness of the absorber thing. And so, now we know X A is going to be with the design absorber 50 Newton divided by this, which is equal to or equivalent to 8.64 millimeter. and we know that our limiting value is 7.5. So, this is more than 7.5 millimeter. So, this condition is not being satisfied. So, we cannot use this. So, we have to now do the design again. Now, this is a training in design. A mechanical design is not a straightforward problem where applying formulae and finding out values. It is always trying to fit in the constraints along with the desired conditions to be satisfied. So, here we have found that starting from this, it will not be possible. Now, one thing, should we start satisfying this condition? Now, without going through the calculation, I can tell you, and one can verify that if we satisfy this, then the lower value of omega n which will be resulting the way we have found out will be more than 1350. That means the frequency condition will not be satisfied. Therefore, let us not start from that side. Rather, now let us try to see if we satisfy the rattle space, what happens. So, this is the second design mass, let us, or second design attempt, let us say. So, our next attempt is so now let us start designing the absorber starting from the rattle space condition. That means let x a d be exactly equal to 7.5 millimeter. Now, with a 50 Newton force, so this is nothing but 50 or equivalent to 50 by K A into 1000, where K is in Newton per millimeter. So, this will give us the value of the stiffness of the absorber spring, the final design which we are trying, and this will become something like 6,666.7 Newton. So, once we know the stiffness, we know the frequency has to always match because it is tuned 157 radians. We get absorber mass also will be equal to 0.27 kilograms. Because Ka by Ma is equal to square of this. So, we can easily calculate and you find out. Now, once we get this, we can find out the value of nu. What will be the mass of the system? So, with 0.1 kg, nu was this much. So, with so much kg, what will be the value of nu? Obviously, 0.27 by 0.2347 into 0.0446, and this becomes 0.051. So, we have been able to find out nu. Once we know nu, we should be able to find out chi 1. How? We just use this relation, putting the value of nu here, we get chi. When it is minus sign, it is chi 1. When it is plus sign, it is chi 2. So, using this, the calculation gives us and chi 2 will be 1.119, and since chi 1 is nothing but omega n 1 by omega n and chi 2 is nothing but omega n 2 by this. So, directly they will give us the values of omega n 1, which is equal to or equivalent to 1340 ppm and which will be equivalent to 1679. Thus, we find that if we start by satisfying the rattle space condition like this, find out the stiffness of the absorber satisfying this and the resulting MA, because it has to have the same natural frequency as this. Once we know the mass of the absorber and we know for a given mass of the absorber what was the nu, we can find out what should be the nu in this case. So, for example, if we had nu here with this, the mass of the system, I think we can easily find out from this without any problem. Now, that means, for example, with 0.1 kg mass of the absorber, your nu we found out trial mass of nu we have erased. Anyhow, we do not require that. So, it was this much 0.019. So, if nu is this much, what will be the value of the original mass or sorry the trial mass with this we can easily find. And once you know nu, directly this relation gives us the chi values, and the chi values are nothing but the natural frequencies divided by the natural frequency of the primary system or the exciting frequency or the absorber frequency, because they are all kept same in case of tuned oscillator. So, this now we find the lower one is below 1350 and the upper one is above 1650. So, it is satisfying the frequency condition also. So, this is just a simple example of indicating that how a absorber is actually designed in the real life situation. It is always a trial and error back and forth process satisfying various constraints. Now, if a system consists more than 2 degrees of freedom, we do not give a separate class as 3 degree of freedom or 4 degree of freedom. What we now consider in general cases of multiple degrees of freedom. 2 degree of freedom was a special case of multiple degrees of freedom. Nevertheless, all the important basic concepts like modes, natural frequencies, that we have already discussed in 2 degree of freedom system, and they will be all applicable in case of multiple degree of freedom system. So, therefore, in an n degree of freedom system, we will have n number of natural frequencies. And n number of modes. So, now it will be necessary, no new concept obviously, but to present or to handle the whole analysis or discussion in a very compact manner, it will be necessary to utilize matrix representation. So, to indicate that how matrix equations come or are written, I will take the simple example of a 2 degree freedom system. So, this is a 2 degree of freedom system. We have already seen this, it is familiar to us. What will be the equations of motion? Equations of motion will be m1 x1 2 dot will be equal to k2 x2 minus x1 minus q1 x1, and we can reorganize and we can finally write, or same thing can be written as m1 x1 2 dot plus k1 plus k2. We have done this before. And for the second mass, we can write in this manner. This is some simple reorganization, and obviously we are discussing the problems of free vibration. Now, how we can represent this set of equations in matrix form? The same equation you will find can be written as so we use second bracket for column matrices and third bracket for square or rectangular matrices. So, you know matrix representation, so therefore, there is no need to explain in detail, but you will find that this is the matrix representing the mass of the whole system. This matrix, square matrix, represents the stiffness of the whole system. This column matrix represents the mode shape, you may say, when it is oscillating, not it is oscillating in a natural mode. This will represent the column of the natural mode of oscillation, and this is the acceleration vector. So, therefore, in compact form we write that mass matrix into acceleration matrix, stiffness matrix into displacement matrix is null matrix, column null, where M is the stiffness matrix, inertia matrix or mass matrix, and if we write or if we take the coordinates from equilibrium position, it will be always a diagonal matrix, and K is the stiffness matrix. This will be always a symmetric matrix. Diagonal matrix also, of course, is a symmetric matrix, because all off diagonal terms are 0. Here the off diagonal terms with this and these two terms are symmetric. That means 1/2 of the matrix, that means above the diagonal term, will be same as the terms in the locations below the diagonal. So, this is a general characteristics of all multiple degree freedom systems. Now, if the system oscillates in a natural mode, with frequency omega and amplitude represented by a column matrix X, like capital X1, capital X2, capital X3. These are the amplitudes of the mass or the coordinates 1, 2, 3 and so on. Frequency is same for all. So, therefore, then you can write the displacement of the system can be written as and obviously the acceleration will be if you substitute in this equation what we get? We get minus omega square cosine omega t has been cancelled because it was common to both terms. Now, pre-multiplying both sides, all terms say, by M inverse. What happened? Then when you do it, M inverse M becomes unit matrix, so it is 1. So, and unit matrix into X remains X plus M inverse into K stiffness matrix Now, this matrix we may call, you can give a name, say A matrix, which we call the dynamic matrix. So, we can write this equation in this form: A x is equal to omega square x for a particular natural mode. Remember, see, if it is the ith mode, this frequency will be omega I and mode shape will be x I. Now, this is a typical equation which is perhaps familiar to you. Now, this matrix equation is satisfied only for specific sets of x's. What I mean to say that when you multiply, there is a column matrix, you multiply the column matrix by a square matrix, you get back the column matrix only with a constant coefficient. This is possible only for some specific column matrices and for resulting some specific coefficient of this value, and this is called the eigenvalue problem. And the values which satisfy this equation here, these omegas, are called eigenvalues, and these columns which are also called vectors. So, these vectors are called eigenvectors, which are nothing but the normal modes, and the eigenvalues are nothing but the squares of the natural frequency. So, this of course can be written in equation form also. And we get a set of homogeneous equations just like the previous cases, and the condition for non-trivial solution will be the determinant of this matrix I is the unit matrix, has to be, which is again nothing but the characteristic equation, solution to which will be nothing but the values of omegas or the natural frequency. So, that we have already seen. So, for each natural mode, that means if natural mode is identified by this superscript I, this corresponds to the natural frequency I, or we can write simply omega I if you do not want to write all the time omega n, because now we will be writing this so often. So, we may write this simply as omega I. Understood? It is understood that this is nothing but the ith natural frequency. So, that n subscript we can now remove from our all the board work. So, if there are n number of degrees of freedom, then I will vary from 1 to up to n. So, n sets of values, that means x1, x2 up to xn, because there are n coordinates, and for the ith mode. This is the natural mode for the ith natural mode, and this corresponds to frequency omega. Now, we can see that these natural modes are really nothing but the eigenvectors of this equation. Now, another very important thing we will find that this natural mode cannot be just arbitrarily anything, and we will now discover some extremely important properties of these natural modes, which will be extremely useful at a later stage. So, let us consider the ith mode for ith mode. What will be the equation of motion? You can see it will be minus omega I square let us call this as equation 1. For the jth mode, equation will be and we call this as equation 2. Now, pre-multiply one by xj transpose. Transpose, I am quite sure you understand the transpose of a matrix, just exchanging the column and rows. So, if we pre-multiply this equation by this, what we will get? Let us call this 3. Now, pre-multiply 2 by xi transpose. So, that equation will be now, it has been already mentioned that M and K are both symmetric matrices. Of course, M is a diagonal matrix, so it is obviously symmetric, but K is definitely a symmetric matrix. So, therefore, since M and K are symmetric, symmetric matrices, they satisfy this condition that x j transpose M x I will be same as x I transpose M x j, and x I transpose x j transpose into K this is a property of symmetric matrix. When a symmetric matrix is pre-multiplied by the transpose of a column matrix and post multiplied by another column matrix, that is equal to the transpose of the column matrix which you post multiplied M, and here it is like this. So, both for M and K this will be satisfied. So, now subtract equation 2 from equation 1, sorry, equation 4 from 3. So, if you subtract this from this, what you will get? Omega j square minus omega I square, because this is equal to this. So, we can write any one of them. So, we will write this j transpose M x I, and this equal to this. So, subtracting it will be 0. So, this is in this case again will not be matrices, they will be values. Now, when I is not equal to j, in general omega I is not equal to omega j. So, the only way this condition can be satisfied is same as now, if this is 0, if you say this is 0, this term is 0, then this has to be also 0. So, it follows So, this is a very special and important property. That means the two different modes, when post multiplied and pre multiplied, both the mass matrix and K matrix, it becomes 0. They are not 0 only when I and J are equal, and they are called generalized mass and generalized stiffness. That means, if I put x I transpose m x I, this will be a quantity which we may call m I, and we can give the name generalized mass. And similarly, x I transpose k x I will be again a non-zero quantity, and we call it generalized stiffness, and this property are called orthogonality of natural mode. These are two very important properties, and at a later stage you will find they will be extremely useful to us. Now, I think our task is generally, as we know, the determination of the natural mode and natural frequency. If we directly solve this and try to get the values, of course, it is fine, and we will get the values as we have already done in one or two cases. However, when a system is large, quite often what happens, a regular normal actual system is modeled in the form of a lumped parameter system, but to make the model very realistic, resulting in acceptable values of the answer, so the number of degrees of freedoms are very large. So, for example, a machine tool or a car, vehicle, all such kinds of actual systems, the representation will be meaningful only when the number of degrees of freedom are pretty large. So, when capital N, that is the degrees of freedom, is very large, then solving this equation directly, it becomes a serious problem. And that is why many methods have been devised which can be applied to simple engineering design problems, and these methods which now we will take up rather than solving the direct equation. And one type of method which we call as iteration method, we will iterate the matrix and we will get the values. That is, of course, a repetitive process, but it converges to the answer after few steps. Only thing that computationally it is far less intensive than solving, say for example, a 10 degree of freedom system, directly solving a 10 degree polynomial is an extremely difficult task. So, we will next take up the methods of solving this multi-degree freedom system. First, we will discuss matrix iteration method, and subsequently we will just discuss some approximate methods for resulting in very quick values, giving an idea about the order of magnitude of the fundamental natural frequency, that is the lowest natural.